Hi, everybody. So I would like to introduce David Keith from Harvard, who is in the area of climate modeling and kind of like climate mitigation. Is kind of the eminent voice on how we can actually overcome the climate problem. He's a very reasonable, has dealt with the technology of climate engineering, the dangers of it, the ethics of it, the political implications of it, the whole thing. And he's here to speak to us about how this technology might contribute to the solution.
Thank you so much. That really was a quick introduction. Thanks very much. It's really a thrill to get a chance to do one of these talks. A real thrill. So here's an outline of what I'm going to talk about. I'm going to really talk about solar geoengineering in two really different ways. One is kind of Platonic geoengineering. So, imagine solar geoengineering in a world that was run by benevolent dictators, not necessarily omniscient, but wise, benevolent dictators. And we can talk a little bit about what solar geoengineering might look like in that world. We'll get to what optimal policy might look like. But of course, that's not really very related to the world we actually live in. So then I'll close by some speculation about what the real risks are, including the risks that come from the fact the world, of course, is not run by folks who are necessarily benevolent. Talk a little bit about scenarios and tensions, and then come to questions. So first of all, what is this idea? Solar geoengineering is the idea that humans could deliberately alter the reflectivity of the planet by some set of technical means, simple cartoon here, in a way to reduce the climate change that comes from the buildup of greenhouse gases like carbon dioxide. So here is a detailed slide of some of the ways to do it. I will not go into details about these, but I just want to flag there's a bunch of ways. They range from putting aerosols, fine particles in the stratosphere, sort of 20 kilometers above our heads. The particles we know the most about are sulfuric acid aerosols, but there's a bunch of ideas for other aerosols that could have different properties, better in some ways. There are ideas for making marine boundary layer clouds, like the clouds you get off the coast of the UK or Seattle. There's ways we might be able to make those whiter and more long-lived. That's called marine cloud brightening. There's ways we might be able to make certain kinds of high cirrus clouds thinner. Low clouds cool the planet by mostly reflecting sunlight back to space. High clouds do that as well, but they also trap heat, and that is the dominant effect. So if you remove those high clouds, you could allow more heat to get out. There's ways that could be really beneficial. And finally, there's ideas for doing this in space-based methods. We've actually started to look at that more seriously in the last year or so. I don't think it's anything humans will do in the next half century, but I think in the second half century, it's not something you would completely discount. So there's a big range of ways we could do this. But what I'm going to do is try and focus on one scenario and its consequences. And for now, I won't give you any justification for that scenario. I'll just kind of jump right in and say what it is. So that scenario is this idea of using stratospheric sulfates, that is sulfur dioxide or sulfuric acid delivered to the stratosphere with high-altitude aircraft, and talk about what it would take to do that and what some of the consequences, good and bad, might be. So as a benchmark scenario, let's say you wanted to do 2 watts per square meter of what we call radiative forcing. That's a measure of how much humans are in the net pushing the climate. And right now we're pushing it with a few watts per square meter in the warming sense from the accumulated greenhouse gases. So if we want to do 2 watts per square meter of cooling, if you like, of something that reduces that energy trapping forcing, how would we do it? You need to put something like 1.5 million tons of sulfur in the form of this sulfuric acid into the stratosphere each year. And this could be done using a fleet of something of order of 100 aircraft. There have been several people who've now looked in real detail, aircraft engineers, at what it would be like to do that. These would be new build aircraft, but really using existing engines, existing commercial design standards as sort of a 100,000 or so flights per year, and the annual direct cost of order 5 billion. I mean, a lot of these numbers have big error bars. Maybe it's 10 billion, but as you'll see, that really is nothing compared to the scale of the cost of the climate problem, which is not a claim this is a good idea. It's just a fact about it, for good or bad. So the obvious thing is, what do you want to compare that to? So I told you that we're going to talking about putting 1.5 million tons a year of sulfur in the stratosphere. Is that big or small? Well, one thing to compare it to is what a volcano does. Not every volcano, but some volcanoes have a cloud that actually gets sulfur into the stratosphere. And that sulfur, that visible cloud isn't the thing. It's the sulfur, SO2 gas that turns into sulfate aerosols in the stratosphere that actually cools the planet. And Pinatubo, this big volcano in 1991, did actually cool the planet by a order of half a degree. And it did it with about 8 million tons of sulfur. And the current global emissions of sulfur into the lower atmosphere, which, by the way, kills sort of order a million people a year, is about 50 million tons a year. It's going down quite quickly now as we regulate sulfur air pollution better. And also, it's useful to sort of think about it that when you think about these costs and number of aircraft, there's sort of 40 million commercial flights a year, and the cost of climate impacts in 2100 are of order of few percent of GDP, so kind of trillions. So these costs, for good or bad, are really pretty small compared to climate. So where would we put it? The stratosphere is stratified. Things don't mix well. The stratosphere, if you like, you could think about things sliding over each other because they're very dynamically stable. And there's a slow circulation of the stratosphere where things tend to rise in the equator and sink near the poles. And the boundary between the stratosphere and the troposphere is at about 17 or so kilometers in the tropics, and then much lower in the extratropics. So when you fly between North America and Europe, especially in the winter, you're well into the stratosphere, but not when you fly across the equatorial Pacific in a regular airplane, which flies at 10 kilometers or so. So the idea is as material will be injected in this region labeled here, the injection region, and we're pretty confident that if you do that, you will get a relatively even coverage of aerosols. There's tons of modeling, but also some real observations that back that view up. So let's first talk about some of the direct impacts of that benchmark scenario. So these are the side effects, the unwanted side effects. So first of all, the ozone layer, the stratospheric ozone layer that protects the Earth from otherwise being sterilized, that ozone layer has been damaged by chemicals humans put there, most of all the chlorofluorocarbons, chlorine-containing compounds, but also nitrogen oxides. And in ways that are too complicated to explain right now, it turns out that adding sulfuric acid accelerates those reactions in some ways. The sulfuric acid itself doesn't do much, but in the presence of the chlorine that humans put there, you make that stratospheric ozone loss worse. So you can kind of estimate what that is and get some estimate of the net impacts of that on mortality on the surface. Secondly, you got to think about air pollution, obviously. So one of the biggest overall global environmental problems today, climate change is in terms of direct impact on humans, is really air pollution, not climate. Climate will be a much bigger impact over the century. And so it's worth really asking yourself, if we're talking about adding additional sulfur to the atmosphere, what is the impact of that sulfur? So it turns out we have pretty good models that were developed to estimate the environmental impact from aircraft. And I collaborated with a group that's an expert in those, and we've come up with some numbers with big error bars, at least 50%, but it gives you a sense of it. And again, you can think about the comparison. So the current estimates for global mortality from outdoor air pollution are of order 4 million, big error bars there too. And to give you a sense of it, even with air pollution, even with air conditioning, even with all the ways in which a rich society like the US is relatively isolated from the effects of heat stress, the estimates are that with what's called a business as usual climate scenario, warming alone brings an estimated something like 60,000 annual additional deaths in the US alone late this century, give you a sense of that scale. So this gives you a sense of some of what physically this benchmark scenario would mean and what its direct impacts are. Now,
let me ask you a question from Fraser Kirkman for
sure.
Specifically this. How much do you actually know about sulfur injections and regular sulfur injections and the actual health effects?
A huge amount, because sulfur has been so important as an air pollutant. There are literally thousands of scientific studies now over a good chunk of a century. There's a really detailed, what's called the Harvard multi-study city, no connection with me at all, but it was done at Harvard, which has really done this great epidemiological data that estimates the years of life lost by an additional amount of particulate matter, something like an actual year of life for 20 micrograms per cubic meter. And I think we actually know that pretty well. And this is not a new environmental battle. The first scrubber on a coal-fired power plant that was there to reduce the damaging effects of air pollution was on the Bankside plant outside London in the century before last, that is at the end of the 19th century. So there's a long problem. So this gives you, and also sulfur in the stratosphere, because of volcanoes and because it's a dominant aerosol in the stratosphere, there's been a less history, but a long history of studying the dynamics of sulfur in the stratosphere. So now some evidence about what this benchmark scenario would do to reduce climate risks. So I'm going to claim, and I think there's real basis for it, I'll get to that the evidence is strong that it would reduce hazards like regional changes in availability of water. So climate change from long-lived greenhouse gases like CO2 makes some areas relatively drier and some areas relatively wetter. And the evidence is strong that doing this benchmark scenario, solar geoengineering, would reduce those changes, bring most places back closer to the pre-industrial. It's quite effective at reducing extreme precipitation. And one very important version of that in the tropics is cyclones or hurricanes. And it turns out that when you cool the world with this solar geo, you have a stronger effect in dampening tropical cyclones than when you cool the world by reducing CO2. It reduces the regional changes in extreme temperatures, and these extreme temperatures are one of the things that have the biggest direct impacts on human health. And I'll give you a sense of this cyclone. This is from a model that's been developed that has much better representation of cyclones. To give people a sense, I got a bunch of modelers here. When I was first playing with the Fortran of climate models back, 20 some years ago, almost a quarter century ago in NCAR, none of these models directly got cyclones right. We kind of had a cyclone subroutine. But now the basic physics of these models spontaneously generates cyclones in an amazingly accurate way. The plot on the left shows that with this high resolution model from GFDL, you get really the right distribution of cyclone intensity. And that's really not done with a lot of tuning. That pretty much comes out of the model physics. And that really says something strong about the way these models are really getting better at capturing the core physics, especially of precipitation and intense precipitation. So we collaborated with people who run that model, and we ran that model in the standard 2 times CO2 scenario shown in red here, and in a scenario where you do 2 times CO2 and roughly 1% less sunlight to simulate solar geoengineering. And separately, we've done it with much more realistic simulations, and lots of other groups have that actually have sort of sulfur in the simulated stratosphere. But I'm showing you results from the very simplest version where you literally change one constant in the model, the solar constant. And what you see here is that if you look at, for example, the change in surface air temperature, that's the global warming, you can see the median change under 2 times CO2 is sort of 2.5 degrees C. That's the standard global warming we all know about. And the worst affected places have warming up to 4.5 degrees C. This is just really, really terrifying. And what you see is when you do this enough solar geo to cut the mean in half, you see that the extremes are really reduced a whole lot. And that's true for surface air temperature and precip minus evaporation, which is kind of water availability and so on as well. But this shows you the distribution over all land surface points. It doesn't tell you the politically really important thing, which is, are some regions made worse off? Looking at this first graph of surface air temperatures, if it would turn out that some regions moved from being on the very cold side here, the least affected under 2 times CO2, to being more affected under 2 times CO2 and solar geo, they wouldn't be happy because they'd be made worse off. And politically, what matters is whether some regions are made worse off. It's one of the key things that matters. So we looked at that directly. And we looked at that by using a standard division of the world into regions that you can see here. This is a IPCC's SREX division using very standard methods of doing the stats. And we looked at these 4 variables: temperature, extreme temperature, water availability, precip minus evaporation, and extreme precip. And for each of those regions, we're asking whether the world with CO2 and solar geo is moved further away or closer to the pre-industrial. So we say that things are moderated if the variables move closer to the pre-industrial. That's closer to what happens when we run the model without CO2 or solar geo, or whether it's moved further away, exacerbated. And then, of course, we tag it for statistical significance. This is a big, complicated plot, and we're being careful to use moderated and exacerbated, not just better or worse, although in practice, that's more or less what it would probably mean for most regions. But that's a value judgment. And the really interesting thing from this paper, but this has come out of a lot of other papers, is in this particular case, not a single one of the symbols of the all those regions and all those variables, not a single one of them is coded bright red. That is, not a single one of them is significantly exacerbated. Now, I'm kind of guessing this is too good to be true. And I can show you a bunch of results that are a bit different, but it turns out to be systematically correct that a moderate amount, so like we showed here, half solar geoengineering, does tend to reduce major climate hazards, not just temperature, but also extreme temperature, changes in water availability, et cetera, essentially everywhere, and makes things exacerbated worse almost nowhere. And that's really a kind of amazing result, and a result that's been robust across a bunch of climate models. And I think if there's a single reason to take solar geoengineering seriously, it's not this paper that I happen to be an author of, but this set of papers that the community's come up with, and the fact that there's no real paper that asks the same question and gets a really different answer. So it also reduces sea level rise. That's no big surprise. It reduces carbon concentrations in ocean acidification. That may be surprising. Indeed, it's common to see in the kind of press literature that solar geoengineering will make ocean acidification worse. That might be true for this moral hazard reason we'll get to when we talk about solar geoengineering as something closer to the real world. But if you just think about the pure, forget about human responses and just think about what this does to climate, there's a thing called carbon cycle feedbacks, that carbon emissions mean more carbon in the atmosphere, mean a warmer world, and a warmer world means less carbon is absorbed by the ocean. That's a simple thermodynamic effect. And say more carbon is released from melting permafrost in lots of other cases, and that's a feedback. There's lots of uncertainties, but that's in all standard models. No big mystery about that. And so if you imagine two different worlds, both of which have the same human emissions of CO2, but one world has some solar geoengineering, so the temperature response is a bit less, then in that world, with the same human emissions of CO2, there's actually a little less CO2 in the atmosphere at the end of the century because there's less of these carbon cycle feedbacks, and so therefore a little less ocean acidification as well. It's not a big effect, but it's not a zero effect. And of course, these things reduce global average surface temperatures, which is sort of the one thing everybody knows that solar geoengineering could do, but the question is what else it does. So why should you believe any of this? There's multi-model comparisons from these 12 geoengineering model intercomparison project models. But I think the big thing is after actually now about 20 years since the first climate model study of solar geoengineering by Ken Caldera and co. And combined with the fact that the scientific community has a strong and I think a very healthy bias to look for problems, there's no really strong evidence that contradicts any of these conclusions if you assume that solar geoengineering is implemented in this even-handed way I'm talking about. We'll get to what might happen in the real world later. So now let's talk about optimal policy, still in this kind of platonic world. So let's step back and think about climate change, the climate problem overall. This is a simple schema of what the climate problem looks like, and here's a more complicated versions. The economy drives emissions of carbon dioxide. That's the amount per year, so like 10 billion tons of carbon emissions roughly per year nowadays. Drives concentration. That's the amount of CO2 in the atmosphere, which we measure in parts per million. So this is this number that's at 410 or so parts per million now. That drives these long-lived climate changes, and that drives the human and ecological impacts. So how do we intervene in that system? There are basically four ways. First, and by far most importantly, nothing I'm talking about for solar geo changes the fact that we must decarbonize. The first thing we do is we decarbonize, which breaks the link between the economy and CO2 emissions by changing the underlying industrial infrastructure of the planet to use carbon-free power, to use renewables or nuclear power. Second, we could remove carbon from the atmosphere. That essentially allows us to go back in time, to go back, to undo the effect of past emissions. There's a whole bunch of ways we could do this. All of them have significant costs, and I believe environmental impacts, but I think there's no fundamental doubt it could be done. Then there's solar geoengineering, the subject of this talk. And then there's adaptation. All the myriad ways that we can lessen the local effect of whatever climate change there is. And that ranges from things that are really high tech, like more genetically engineered crops to have more drought resistance, to social adaptations that can be very, very important. I was visiting Bangladesh in January at a big conference on climate where I was invited to talk about this topic because the poor world wants to own it more. And I got to travel in some of the poorest parts of the Delta of Bangladesh. And understand more now that while there have been some terrible cyclones in the last decade, they've killed hundreds of people, which is huge, but enormously less than the roughly 500,000 people that died in the cyclone in 1970 or 71, whatever it was. And that's most of all because of all sorts of adaptations, including cell phones and warning systems that get people into cyclone shelters, which are basically just schools that don't flood. So all these things have a big impact. So what's an optimal way to think about mixing decarbonization, carbon removal, and solar geoengineering over time? That's going to be the focus of this part of the talk. So first of all, let's just talk without units about just the way these variables link together. So first of all, if you just emit fossil fuels forever, climate risks grow without bound. Pretty obvious. What people often forget is, of course, the flip side of that is if we bring emissions to zero, we don't solve the problem. We just stop the problem getting worse. We stop the accumulation of emissions. And some parts of the problem, like, say, sea level rise, will actually keep getting worse for a long time. Other parts will start getting a little bit better slowly. But to first order, the climate risks are proportional to cumulative emissions. So stopping emissions, bringing net emissions to zero, this giant hard task that we all should be focused on in climate, that doesn't eliminate the problem. It just stops adding to it. So it's possible to remove carbon from the atmosphere, and that can reduce the kind of underlying driver of climate change. But I think it's inherently something that's slow and expensive, and I think we do mostly after we've cut emissions. And then my view is that if we use solar geoengineering, which I don't think we know whether we should or not yet, it's used to kind of slice the top off. It's used to flatten the curve in the COVID lingo. Okay, so that was a graph without any numbers. Now I'll show you some early versions of a version with numbers. So to do that, we have to have some model that captures the optimal dynamics. And this is where this idea that we're trying to simulate the optimal for humanity comes in, essentially what a benevolent, wise dictator would do. So we're building on Bill Nordhaus's dynamic integrated model of climate and the economy. It's the first so-called integrated assessment model. It's the one of the things that contributed Bill Nordhaus winning the Nobel Prize last year for economics. There's a simple diagram of what's in this model. You look at a diagram like this and you have no idea about the level of complexity underneath. What I like about the DICE model is the level of complexity underneath is very low. And the reality is all these things, or almost all of them, are deeply uncertain. So while there may be some folks in the Google world who want to build very complicated integrated assessment models with more and more details about the exact dynamics of some parts of the energy economy, the reality is our ability to predict anything meaningful about economic growth or technology over 100 years is really pretty lousy. So I like this model because it's very simple. And it's been one of the kind of models that people have built on and adjusted over the years. And I and some collaborators have built on this model to add carbon removal, which the base version didn't have, and to add solar geoengineering. And I'll tell you a bit about how we did that. But first of all, some idea of what's in this model. Because again, a diagram like this, you've got a so-called climate model in there, but what is the climate model? It's ridiculously simple. Those are all the equations, literally, of our climate and carbon cycle model, not of the Nordhaus DICE model. You can see actually the tiny modification in red there is our carbon removal from CDR, which we added. So it really is that simple. And this shows you the marginal abatement cost at a fixed time. It actually varies with time in a way that we didn't alter in the model. And that shows you the way we have marginal abatement costs for mitigation and for CDR in our modification of the model. CDR is carbon dioxide removal. So that's the kind of core thing we did. And then we had to put in solar geo. But how to do that? We really don't know very well about what the downsides of solar geoengineering are. And we need a simple, parsimonious way to capture the weaknesses of solar geo. So here's what we do. This is that same graph I showed you earlier, same plot. But if you look at that plot, I showed you the plot just for enough solar geo to half warming, but there's nothing magic about halving it. We could do enough solar geo to do only a quarter warming or an eighth warming or full warming. And this top graph here shows you the way some variables, temperature or P minus E, the way the RMS, that is region by region, root mean squared anomaly change varies. And what you see is that for some variables, especially P minus E, there's a point where things start getting worse, whereas you do more and more solar geo, you actually start making the normalized anomaly worse because some regions are really getting worse off. And it turns out you can think about this in a kind of vector representation that really is pretty convenient. So if you have two regions or two variables, CO2-driven warming will change those variables differently. So, CO2-driven warming has a different effect on temperature in San Francisco than it does on rainfall in South India. Makes both of them go up, but in different ways. And solar geoengineering might change both of them, but again, in different ways. But both these things are, to a good approximation, linear. So we can choose how much solar geoengineering is. That's the length of that red arrow. We can make the red arrow longer or shorter. That's a policy choice. It's a very slow policy choice about what we do about the blue arrow, how much CO2 there is in the atmosphere. But right now, we're just thinking about the red arrow, how much solar geoengineering. And the right answer, of course, might be to do 0. But the point is that you can choose, say, to do enough to make region B exactly back to pre-industrial, but then you leave region A with quite a lot warmer. Or you could choose some kind of optimal that minimized the root square, the distance between the two. So that was in two-dimensional space. And of course, these are just diagrams. This angle is made up. The question is what the angle is actually. But that's in two-dimensional space, but it works equally well in any number of dimensions. So it turns out for that whole climate model response and all these different variables, if you make that linearity assumption and you assume that damages are proportional to the square of the deviation from pre-industrial, which is a common and I think robust, but not necessarily correct assumption. If you assume that, then you can boil down all of the question about how the climate responds to solar geoengineering to one number, which is really just this angle. It's an angle in degrees. So if the angle in degrees was 0, it says that solar geoengineering perfectly opposes CO2. It says it's anti-CO2, and you can make all variables back to 0. If the angle was 90 degrees, it says that solar geoengineering is just a different forcing, and it doesn't really make things better in the mean. And the question objectively is, what is that angle? It's a single number. So that's how we have characterized things in this model. And here's results. So this is results from our model for a 30-degree angle. And these are these results for the optimal radiative forcing, and this is also showing you temperature. And what you see here is, first of all, the top line is really what business as usual or unmitigated climate change would happen. So that's in the Nordhaus model. If you don't have any policy, so you don't have any reduction of emissions, you have no carbon removal, you have no solar geo, you follow this trajectory, which gets you up to 10 watts per square meter late in the next century, just absurd amounts of climate change. And then this shows you in this particular version how the model has optimized. So the model has started mitigation now and gradually built it up. It started CDR only roughly after the peak, and it started solar geoengineering at the beginning. So what I'm also showing you here are in that model, but this is a very standard model. It's used to calibrate, say, the US cost of carbon and so on. It shows you the policy cost and damage cost. So I'll show this for a few different angles. So this is for angle 0, although we still have some damages from solar geoengineering. And so for angle 0, the model pretty much just does solar geoengineering. I don't think the real angle is 0, but it just shows you what the model's doing. For angle 10%, 20%, 30%, 40%, and at 50%, 50 degrees, you basically back to almost the case as if you had outlawed solar geoengineering in this model, where you get this combination of mitigation and carbon removal, and you get a much higher peak temperatures, 3.5 degrees peak temperature instead of the kind of 1.5 degrees you get with 30 degrees. So what's the real answer? We don't know. That's what we have to do the research for. But I would say that you could defend the idea that angle was actually as small as 10 degrees, which provides this giant benefit in terms of reduced damage and policy cost for solar geoengineering. And you could defend that by saying that there's a lot of evidence that one of the dominant risks of climate change is extreme temperatures, and solar geoengineering directly goes after those. Who knows? I'm going to skip through this because I'm going a little bit slow. And I want to end this part of the talk, and I've got just the last little bit, by pointing out that all of this is in some world that looks a bit like the kind of psychohistory of the first foundation for those of you who like, second foundation for those of you who like science fiction. It assumes this world where everybody is rational, where there's one rational actor, where that one rational actor is making omniscient decisions for the world. And that is underneath all of these standard models of optimal climate policy. And it's important to say there really isn't necessarily that much to do with that world and the world we actually live in. So let me say a little bit more about the world we actually live in.
So before you get into the Hobbesian view, if we had full control, what knobs do we really have? So we have, I mean, you described, emit less, remove stuff, solar geoengineering. Do we have other knobs? For example, the Gulf Stream is being killed off no matter what we do with these solutions. Can we just fix the Gulf Stream or the monsoons or something like that? Do we have additional knobs we can play with?
So the Gulf Stream isn't being killed off. The Gulf Stream is mostly driven by the wind-driven circulation, and that doesn't change that much. So that's actually a bit of an overclaim, I believe. It might be possible to do some versions of solar geoengineering that target particular areas like monsoons. I think the question of whether that's better or worse. So in a world of a globally beneficent person, then presumably having the ability to do local tuning is a plus, or even weather control is a plus. In the real world, it might not be. Think about two extremes. In the world where every region can choose its own climate, then there's no political problem. Each region just chooses its own climate. But it's fundamentally impossible to do that. The climate of the Earth is interconnected by flows of heat and momentum and constituents. And so doing something in one area, even if you only do the solar geoengineering in a single area with some amazing space-based scheme, you necessarily have effects in other areas. And same with weather control. And in the world with competing self-interested actors, states, you could really get bad outcomes, I believe. So this gives you some sense of what some famous people have said about solar geoengineering. And what's under all that view? Lots of things, but I think the single thing that's most under it is fear of what's often called the moral hazard. I think a well-justified fear that people will exploit talk about solar geoengineering to avoid emissions cuts. So let me get to that by talking a little bit about the risks, and I'll close the rest of this pretty quickly. So here's just a big messy list of potential risks of solar geoengineering. Here's a way to organize it. And the way I think about the risks is really in four categories. One are a whole host of physical risks of relatively well-intentioned wise use. That's the risk that would still be there if we were trying, if some group of people was commissioned to use geoengineering with a goal of trying to reduce climate risks and even had the global way. There'd still be lots of risks, and this is some of them. And the exciting thing is now there's actually research on almost all of those, at least a little bit. But then there's risk of deliberate misuse, risk that these technologies are used by one country to try and make another country worse off deliberately, climate wars, if you like. That's a completely different category. Then there's risks that are often called the moral hazard or the mitigation threat, the risk that just talking about these technologies, just researching them, even if not implemented, just making them look good, as you might argue I'm doing in this talk, reduces the incentive to cut emissions, makes it more likely it will kind of be addicted to fossil fuels, and that will make the underlying problem worse. Then there's problems related to the fact of what it means to kind of take over natural processes like this and what it means for our relationship with the natural world. I'll just say a few more comments about scenarios and about some of the tensions involved. So there's a kind of tension between the realpolitik view and the United Nations view, where there's an attempt now to develop through the kind of UN system understanding of climate, but also understanding now of solar geoengineering through the IPCC, through the UN Environment Assembly, a bunch of other agencies. And I think it's fair to say this is a very slow-moving process that's governed by consensus, and it's not likely to produce a sharp answer, either to ban solar geoengineering or to implement, is my guess. Separately, there are nations that will feel real harm from climate change, and they may be motivated to want to implement these technologies to reduce the direct risk to their citizens by, think of an extreme heat wave that kills lots of people in South Asia. There'd be countries that would take seriously maybe implementation, or the US. So how does that play out in the real world? And that's why I'd like to talk more about it in the Q&A part of the talk. And I think I'm running a little late, so I want to end this really in just two more slides. I want to point out there's this tension that we can talk about in the Q&A between the kind of realpolitik world and the United Nations world. There's a major tension in solar geoengineering, I think, between the rich and the poor. The rich who've driven the carbon emissions that are driving climate change, and the poor who suffer the most. And the question of who really is in control of a technology like solar geoengineering, a technology that's cheap and that is in principle quite widely available to different governments. Then there's the fact that governments are not the only things in control anymore. There's arguments that the power has been actually diffusing away from governments. So governments interact with businesses, international businesses that have power, I think in many ways more power than they should, and civil society organizations, big environmental groups that also have transnational power. So it's not just a world of governments, it's a world of other entities as well. So just to maybe end on this slide, I think the big questions are about all this research are, how confident should we be that any of the results of the kind I showed you were true, given the small number of people doing research on them? Might there perhaps be some deep bias in climate models that makes solar geoengineering look far better than it really will be? Is some of what I'm showing you groupthink by people like me who worked on this problem too much? And how do we learn more about it? And particularly, how do we learn more about it in a way that reduces the probability of a kind of slippery slope that inevitably leads to deployment? My view is there's a strong case for us doing more research, but we don't want to do research in a way that doesn't automatically imply decisions about future deployment. Thanks very much for listening. I look forward to Q&A.
Well, thank you very much. And let me pick up a few questions off the chat, so which are willing to be clarified quickly. Which is one is again, Fraser Cookman asking, to what extent is climate engineering is a replacement for dealing with carbon? And can we just become addicted to it?
So as a technical matter, it's not a perfect replacement. So the underlying climate risks grow with a cumulative amount of carbon, period. And solar geoengineering may sort of reduce the coefficient, meaning that there's less risk for a given amount of accumulated carbon, but it's still true that it grows with accumulated carbon. So if you said, we're not going to worry about cutting carbon emissions at all, we'll just keep letting carbon emissions go, which means carbon concentrations grow without limit, which means you have to keep growing solar geoengineering without limit, you then are walking the world further and further away from the pre-industrial to a world that's sort of dangerously poised between two opposing forces, this cooling force from solar geo and the warming force from greenhouse gases. And that is a more and more dangerous world as time goes on. So I think there's no way that solar geo can substitute for emissions cuts. The way I think about it is it can supplement emissions cuts. So emissions cuts plus solar geo might produce a world with less risk than emissions cuts alone.
Right, and I think you point out in other, like in your book, it's like ocean acidification and that kind of stuff. It's completely not solved by this. So we have to deal with it by
10% level. That's right.
Right. And then the other question is, if we start doing this, how long would it take for us to know whether the actual technique is working?
So we would never, in the real world, there would be big uncertainties about what the actual effects are with solar geoengineering, even after we did it. And that should in a way be obvious when you think about it, because there's big uncertainties on what the effect of CO2 is, even after we've done it. And that's because we've got both noise in our observational system, but the underlying climate system is noisy. It has internal variability. So even though have warmed the planet with CO2 and we're warming it faster, and no sensible person doubts that CO2 is now an important driver of climate change, we can't just look at the record and figure out exactly what the effects of CO2 are. And the same would be true in a world with solar geo. If you do solar geo, you'll be able to argue through models, supplementary observations, that there would be less climate change than there would have been otherwise. But you only have one world. You only have one pathway, if you like, through the 20th century. And attribution of exactly how well things are working and what part of some bad effects are due to solar geoengineering or other things, that attribution will always be hard. And it'll always be model dependent.
It makes sense. So then moving back to the more political aspect of this, okay, let me do just the nastiest one. So for example, when people do computer security research, it's to figure out if a hacker were to break into a system, what would happen, right? Yeah. So now if I imagine, let's say Russia says that global warming is awesome, we're going to terraform Siberia and just goes, all in on carbon. And India says it's awful, we're going to go all in on solar geoengineering over India. Or what kind of collective decision or game theory games are being played by these actors?
So I'll give you one interesting game theory way that says how different the solar geo problem is from the CO2 reduction problem. So for CO2 reduction, the bottom line is the benefits of CO2 reduction are global and far in the future. And the costs are local. It costs money to decarbonize your economy in general. So it's to each country's strategic advantage in a kind of game theoretic multiplayer prisoner's dilemma game, to each iteration of the game to say how much you really care about the whole world and how much you want to act together collectively, and we're really going to cut emissions. We know we didn't do it last time, but we're really going to do it the next cycle, and then not do it. And I was part of a game simulation of how climate negotiations would play out. A friend of mine ran a game like that in the early 90s. And that's how we played it. And that's pretty much what's happened since the early 90s, is countries make grand claims about what they're going to do, and then they mostly don't do much. Changing now in some hopeful ways. So solar geo is deeply different. The cost of solar geo is near zero, we believe, but the effects are pretty global if you're assuming that kind of solar geoengineering. So let's say you've got a spectrum of different amounts that each country wants. Maybe there's 10 countries, and maybe half of them think that the right amount of solar geoengineering is zero based on their estimates of damage to them, and some of them want 2 or 5 or 6 in some units. The default game theoretic expectation is that the country that wants 6 gets it because it's free to do it. It just does it, and it gets the right amount, and everybody else is oversupplied. So what that says is that for a public good problem like carbon reduction, the game theoretic expectation is that the public good will be undersupplied. We don't do as much emissions cutting as we should. For a public gob, as Marty Weitzman called it, like solar geoengineering, where it's sort of partly a good and partly a bad that depends on who you are, but it's cheap to implement. Then the expectation is that it'll be oversupplied. And so I think that is one of the worries about solar geoengineering, is people will do too much of it.
Okay, so then Shantanu Baraj mentions an interesting twist on this, which is the data is going to be really messy. So COVID is an example where we are still arguing about the actual impact of a disease where we have pretty decent data. And this is going to be much, much nastier for all actors. So how does lack of forecasting play into this?
So it is and isn't. I mean, the question of whether it's a harder problem is complicated. So it's a much slower moving problem. But if you're talking about, say, how much global radiative forcing you were actually getting from a given amount of sulfur aerosol in the stratosphere, or what the distribution north to south was of that radiative forcing, that's something where my guess is if we were actually doing solar geoengineering in different potentially competing countries with their scientific teams would have different views, the views would actually vary a lot less than the views about COVID. There's some ways in which COVID is, I think, actually a more complicated thing than certainly radiative forcing. The underlying attribution of climate change is hard, but again, the range of models, I think, is in some ways small in the range of models for COVID. They're important analogies, but it's also a very different problem.
Okay, interesting. So we have a few questions like Catherine Benderberry asking kind of the trade-off between the warming aspects of climate change and all the other effects. So we talked about ocean acidification, but there's other impacts of carbon that are not isolated. And of course, we have species laws that are just us taking things over. So how do we balance all these effects when we have pretty limited levers?
So that's why I was very careful in the talk to point out that solar geoengineering doesn't just do temperature. So in my view, solar geoengineering shouldn't be focused just on temperature, and it doesn't only affect temperature. And in fact, the evidence is that it affects lots of other variables: sea level rise, water availability, et cetera. And collectively, we need to think about those climate impacts, not every single one, but we need to think about the ones that have the biggest impacts on people. But I would say, in fact, there is significant evidence that extreme temperature, which isn't the same as temperature, but extreme temperatures are one of the biggest impacts on humans. But so short answer to that question is solar geoengineering, in fact, does a range of things, good and bad, not just temperature.
So let's drag that one out. So what kind of the impact? I mean, we have heat stress, but more broadly, I think agriculture is probably going to be the biggest one. Is that right? And if so, how bad?
Yeah, so heat, but I want to stick with heat stress for a second. I mean, some of you may not be aware how good the epidemiological data has got over the last decade. It's been one of the most exciting things that's happened in the climate space. This isn't about solar geo. That it really shows that economic and intellectual productivity are reduced by extreme temperatures. And that's true if you look at within countries. It's true if you look between countries, and there's good physiological experiments where you put people in rooms at different temperatures and get them to do physical or mental tasks. And the effects are pretty strong. Sort of an extra degree C peaks, give you kind of a % less GDP. And there's a lot of evidence that that's real and it's long run. It actually reduces productivity. And sorry, your other question was, so that was about
agriculture.
Yeah. So agriculture is a tough one. I'm actually a co-author, a minor co-author, of a big paper right now that's tried to really use the best agricultural model that's now in a climate model to look at 3 different kinds of solar geoengineering and to basically compare how solar geoengineering compares against emissions cuts as a way to move the world from this so-called RCP 8.5 business as usual to a more middle ground RCP 4.5. So to cool the world, if you like. And what you find, which shouldn't be much of a surprise, but I think is to some people, is that from this model, and we didn't fool with it, and there are other papers that back this up, geoengineering is actually better than emissions cuts in terms of protecting agricultural productivity. And the reason is that plants do benefit a little bit from that extra CO2 in the air. It reduces their water stress. It's not a black and white thing, and there's some disbenefits, but in the net, that's relatively robust. So if you compare 2 worlds, one of which where you've reduced the net temperatures a little bit by having less CO2, and the other one which you've reduced the net temperatures a little bit by solar geo, that second world seems like it has a higher agricultural productivity.
Okay, cool. So then let me focus then on, let me see, concretely, there's a comment by, Mark Waschenberger about the actual economic model used, because now we're talking about the agricultural impacts, the productivity impacts of people, but your basic model is the Nordhaus model, which is fairly simple. So some of these things, actually in the other comments, he points out that in Nordhaus model, 6-degree impact, a change in temperatures hurts GDP by some moderate amount, but not an insane amount, whereas 6 degrees should be catastrophic. So how do you account for it properly? And you're pointing out Nordhaus is simple, as they show a benefit of that.
Yeah,
but it's missing a ton of stuff.
So I think the big and not intuitive result is about the order. This is the slides I skipped. It's about the order of operations, if you like. So if you look at sort of the public debate right now, everybody except some of the oil company troglodytes agree that we need to cut emissions. We're not doing it fast enough. I think there's broad agreement we need to do it. There's now lots of talk about carbon removal. If anything, I think it's a little bit overhyped right now. And there's this idea that we're going to do massive carbon removal in the near term to keep under 1.5. And in general, the assumption about solar geoengineering is that it's too crazy to talk about, or if we talk about it, it's something for the distant future. But the, I think, quite robust result from that modeling is that it makes sense to implement solar geoengineering before large-scale carbon removal, after emissions cuts. You start with emissions cuts and you just keep ramping them up. But you don't really do large-scale carbon removal. I mean, you start doing some, but you don't do large-scale carbon removal as a way to really draw down concentrations until you've cut emissions to near zero, because in general, it's cheaper to not emit a ton of carbon than to emit it and recapture it. Not perfectly, but it's certainly true for the first 2/3 of emissions or something. And solar geoengineering, if you just believe the models, you should start yesterday. Now, of course, in the real world, I don't think you should. So in the real world, I would not vote to start solar geoengineering today because I don't think we know enough. I would vote to have a really serious international open access research project. We need a real kind of, it's now not a very good word to use, but a red team, blue team kind of approach where there's some teams looking at how to do solar geoengineering in a way that has the least risk, is most controllable, has the greatest benefits, and a whole lot of other teams looking at all the ways it could fail and really trying to pick it apart. That's the only way you get robust confidence in something. And I think even if with a really big research program, I don't see us being in a position to make a reasoned decision about implementation for a decade or more.
So then the obvious question is, what are these unknowns? So when, in particular, I guess for companies like Alphabet, where we can contribute in terms of modeling, what are those questions that can be, helped with?
So I kind of divide the modeling side into, well, there's actually so many parts. On the global climate models, there's a whole bunch of ways in which we can do a better job using the tools we have and the model sets we have to apply them to solar geoengineering. So right now, the total global budget for climate science is of order 6 billion or something. It's 3 in the US. And the total global budget we estimate for solar geoengineering is about 10 million a year. It's near zero. And so we could do much more just applying the tools we have, for sure. But we've already done that for a while. There's 1,000 papers published roughly now in solar geoengineering. I think the really big question is to start looking hard for the surprises, for the unknown unknowns. That thing I put kind of cryptically in my last slide. Are there some deep biases in climate models which make solar geoengineering look better than it really is? So, I mean, of course, you can ask whether there's biases in people like me, but the fact is we didn't fool with the models. The question is there some way the models just inherently make solar geoengineering look too good? I think that's something the community really needs to go after. But then there's a whole bunch of separate questions about understanding actually how to engineer and implement some of these technologies, how you'd actually get aerosols to come out of an aircraft and be well mixed. And there's certainly lots of room for computation there. But I think I want to be cautious about actions by a big company like Google. I think that companies like Google can do work on developing clean energy technologies, better hydrogen fuel cells or whatever, and that can be pretty much just a benefit because there's no big governance problem with hydrogen fuel cells, or only small ones. But with solar geoengineering, the central issue is trust and confidence about who makes a decision, essentially who on earth has the control of the thermostat. And my view is it's really important that be non-commercial and as sort of globally openly accessible as it can be, and ideally not just dominated by the superpowers, by China and the US. I hope that sort of small democracies can work together to do that. And I think there are some, however well-intentioned individual people are at Google and whatever enormous or Alphabet skills people have, I think there are real questions, especially in today's world, about trust of big corporations having an important role in shaping a high leverage, high power technology like this.
That actually makes sense. I think the only probably role for us is to support like the actual decision makers at best.
I think that's the right role. Yeah.
So some of these things you described are more like clarifying the uncertainties in climate models, and some maybe more confuse them or whatnot. But there's questions perhaps of atmospheric chemistry. Are we accounting for all the breakdown pathways? There's one direction which seems to be extremely unknown is how does the biosphere and or maybe even society respond to these changes, and there's more sulfur dioxide in the air or something like this. How much do we know and how much do we not know?
Yeah, so for the biosphere wouldn't, as far as we know, directly see that sulfur in some way. What it sees is this combined set of effects of the climate, of the total burden of chemicals coming down, and that added sulfur is pretty small compared to the current sulfur loading, so it's hard to see that's the issue. And say changes in sunlight are also pretty small changes in regional changes in sunlight from clouds. So my guess is it's hard to see there's really sharp impacts on the biosphere that we wouldn't expect. But again, that's what the hard question is how to go about finding those. I think there are much more room for really unexpected things to happen in the interaction between atmospheric chemistry and physics. So, for a very sort of, I won't go into detail, but there's an odd feedback that some of us have worried about in the group at Harvard. A guy called Steve Wussi's thought a little bit about that there are ways in which if you add aerosols to the stratosphere, they filter back into the lower atmosphere for sure. And there are ways in which doing that in the tropics could actually reduce the natural creation of what we call cloud condensation nuclei from secondary organics. And you could actually get an opposite or negative feedback that was strong in principle. That's an example of a got you that would mean that the main way that we talk about solar geoengineering kind of doesn't work. And that's absolutely something you could investigate with current scientific tools and maybe some more observations, and nobody's doing it. So there's a lot of examples like that, things that are potential big got yous that are, would have a big effect on how solar geoengineering would work, where there just is no serious research effort.
Are there any experiments that they need to be running to clarify some of these issues?
I missed the one word.
Are there experiments we should be running in addition to the theory?
Yeah, so there's a whole host of experiments, both experiments that just teach you that are just learning more about particular parts of atmospheric chemistry and physics that are relevant. So some of the stuff I just talked about, a lot of what we know comes from this experiment called ATOM, where people flew the NASA DC-8 literally from 40,000 feet down to a couple hundred feet off the deck, up and down all the way from the South to North Pole, and filled with a bunch of atmospheric chemistry instruments. And a lot of what we know comes from that, and you could do better versions of that. So there's lots of just better atmospheric science that we need that'll help inform solar geoengineering. And then there are solar geoengineering specific experiments. So I'm involved in developing one of those called the ScopeX experiment that would release a small plume of aerosols, small meaning like a kilogram of aerosols, into a plume that's a kilometer long in the stratosphere from a stratospheric elude payload. And that would teach us something about the aerosol to aerosol collision dynamics and the way things mix in plumes. And that experiment is quite controversial because it's about solar geoengineering, but it's not. Even the critics don't think the experiment itself is high risk. The issue is about what signal it sends about the world moving towards solar geoengineering. And I think my view is it's really important to find a way to do those experiments, but find a way where there's some check and balance that we're not committing the world to implement solar geoengineering, because I think that would be wrong and reckless.
Cool. Well, we're almost at time. Do you want to summarize? Is there a parting message for all of us?
Well, I guess my parting message would be that we need to not be monomaniacs when it comes to climate. It's tempting for the climate advocacy community to focus on the single most important thing in front of it. In the last decade, say in the US or elsewhere, the most important thing has been rolling out renewables like solar and wind, and it's been fantastic. But that alone can't solve the climate problem. And I think there's been a way in which sometimes people in the environmental advocacy community have had a kind of monomania to say, well, don't bother us. We just got to focus on more solar and wind. And I get where they're coming from, because that was the single most important thing. But we also have to think about adaptation and climate resilience. We also have to think about developing carbon removal technologies. And we also have to think, I believe, about serious research into solar geoengineering without committing whether we're going to do it or not. And that last bit, without committing, means figuring out some international methods, maybe even a UN General Assembly resolution, which begins to talk about data sharing for solar geo and talk about limiting or forbidding unilateral action. So I think we need a set of things, both governance and science, that allow us to learn more while still allowing us to make collective decisions in the future.
Awesome.
Thank you.
That makes a lot of sense. It's a very reasonable way forward.
Thanks a lot. Really a pleasure to do this.
Yeah, thank you very much. Have a great day.
Thank you. Bye-bye.
Bye.